they'll capture what's going on the screen and the audio that I'm talking to you. And these videos, they live on YouTube and they'll be accessible through the Moodle area. Now, a word of caution at the start, these recordings are not provided as a substitute for attendance. We are still going to insist and require that as full-time students that you do attend all your sessions. And to be honest, the recordings aren't good enough to make up for not coming, okay? I'm just doing them off my own back, off the laptop. I don't have any technical support. I'm doing them. The quality of the audio and the quality of the video can sometimes not be really that great, but they do provide a useful extra resource to revisit the material after the lectures, and indeed as we get closer to the assessment times or just later on in the unit to do a bit of revision. And any of the I do tend, after today, as we get into the regular rhythm of lectures, I do tend to spend roughly half the time presenting stuff on the screen and half the time working through examples or working through explanations on the paper and pen, which I expect everybody to make their own notes on. But these pages that I produce, I do scan them in and put them in the little comment below the YouTube video as well. So with the audio and the video, hi there, trying to just get a book and sheet to the front. Here. With the audio and video from the recording and the scanned sheets, that does provide a good way to revisit the lectures. Okay. And it is only being done on an experimental basis. There's one or two other members of staff who sometimes do it as well, but at the moment it's not something I think you can expect everybody to do. But you know, it is, hi there, book and sheet to the front there. It is a live issue with universities at the moment, and I think pretty soon we're going to see a lot more of the this idea of recording lectures as well. Okay, enough walking. So the first topic we're going to be looking at is sequences and convergence. Sequences are series and the convergence of these things. And if you were there at the induction activity last week, where we did the activity based on Buffon's needle, let's say Buffon's noodle there, where we all had a sheet of lined paper and these little cocktail sticks as needles, and we were dropping them at random as best as we could, attempting to drop them at random onto the ruled surface. I've got a book and a sheet here at the front. And the reason we were doing that is because we had already worked out that the probability that the needle ended up crossing the line was connected to pi. It was a fraction of pi. It was 2 over pi or something. 2 over pi, yeah. So that's what the probability theoretically should have been. So if we carried out a mass experiment where everybody dropped loads of needles and we look at the amount of times we saw a needle crossing one of the lines and turned it around and divided by 2 or multiplied by 2 or whatever, that should have given us a reasonable estimation of pi. And this graph here shows you the results of that experiment. So the first blue dot was just taking into account, everybody dropped it 20 times. So the first blue dot was just the first person's 20 drops. The second blue dot was the first person and the second person's drops, so 40 drops. So the 10th drop was the first 10 people, so 200 needle drops. So you can see we were, as we got through the first third of the class, we were heading on for some quite good convergence. These dots were indeed getting closer and closer to the level of pi, which is that red dotted line. Something happened with the next batch of students. Maybe, I don't know, they were a bit unlucky, or maybe there was some other effects coming in, okay? Because you have to ask yourself, you know, was everybody's drop really that random? Did everybody really do the 20 drops, or did some people just make up the numbers as they went along? I suspect. Of course, there was this problem as well. We were all sitting at desks that were at an angle, so everybody's needle was falling off, and maybe that was affecting the probability and taking it away from the theoretical one. So that was, you could say, you know, maybe it was converging to pi a little bit at the start, but then not so sure afterwards. But the final estimate we got was 2.74. So that was our first meeting of this issue of convergence. And very broadly, our first definition of convergence is just the idea of having some infinite process getting closer and closer to some final limiting state. Okay? Divergence is where the process does not converge. So where you don't have the process settling down and getting closer and closer to a final limiting state. Now these definitions of convergence and divergence will make a lot more precise when we're looking at them in the specifically mathematical context of looking at a sequence of numbers, which is what we're going to be doing soon. Well, first of all, we will make some motivational remarks about why this might be an important topic and a useful topic to study. And it's important for a number of reasons. Firstly, it is an inherent idea that's kind of intrinsically there in every kind of mathematical modeling process that we do of problems in the real world, be they in engineering, physics, or statistics, and so on. And so every time we look at a real phenomenon and make a model of it in order to analyze it mathematically, of course, the model is not an exact representation of what's going on in the real world. It can't be, because the real world has so many aspects to it, and we can never know everything there is to know about the situation or the precise measurements of everything, etc. So our model is always a bit of an estimate or a bit of an approximation to the truth. So it's not exactly the truth. But that's not a major drawback, because we always kind of operate with the belief that, in principle, the model, if we wanted to, we could make it more exact. We could kind of make it converge to the truth, in a sense. Like spending more effort into taking data from the real world or including more aspects, more features into the model. Okay? So there's this idea that models are approximate, but in principle can be made better approximations of the true situation. In some sense, they can be made to converge to the truth. And just as a little illustration of this, these are by no means exact diagrams, but they're suggestive diagrams. So these relate to the models that are used by the Intergovernmental Panel on Climate Change. So that's a worldwide cooperative effort to study the phenomenon of climate change and to make various predictions about what we might be facing as a planet. And they come out with regular reports showing the outcomes of their analysis, okay? And I guess the main activity they're doing, or one of the main activities they're doing, is they're running computer models of the Earth's climate from the current state that we have now into the future to see what the likely effects under various assumptions, what we're likely to be encountering. So these blocky diagrams here on the left, now they're not exact, but they're suggestive. So we got the first annual report, second annual report, third annual report, and annual report 4. We call it FAR. So these showed the development in the detail in the climate model. Now they're not exact, but the first one is suggesting that the physical model they had of the Earth's surface, so in the computer model, there's some model of the Earth's surface taking into account areas of water, areas of land, the height of the land, and so on. But because of the computer power available at the time, that was a suggestive picture of the amount of detail they were able to represent Northern Europe by. So there's a bit of a green blob for Northern Europe, a bit of a blob for Greenland, see a little bit of Africa down the bottom. We can't even really make that. Maybe Britain and Ireland weren't even represented there at all as a separate one. Okay? But then over the years, as computing power became faster and cheaper, as it continues to do, they were able to, and as the mathematics that they were using in their models became more refined, they were able to increase the level of detail, somehow making the model, in some sense, get closer and closer to the truth. So with the kind of level of detail they were using in the fourth annual report, you see it's quite good. You can see Britain and Ireland, see a lot of detail in Northern Europe. You can see the main mountain ranges, Himalayas there, or maybe the start of the Himalayas, the Andes, Pyrenees, Pyrenees, and so on. So that's some kind of suggestion of a mathematical model getting closer and closer to the truth. And these pictures here are indicating the different effects that they were taking account of. So maybe in the mid-1970s, the computer models of the climate were really only taking into account the energy delivered by the sun, CO2 emissions, and rain. Of course, there's a lot more other stuff going on. There's the actual chemical, by the final detailed models, there's chemical reaction, taking account, modeling the chemistry that's going on in the atmosphere, modeling how the amount of vegetation is influencing this kind of thing, what the actual cloud cover is. This is orange bit, I think, of aerosol, some kind of pollution effect. Okay, so including more and more aspects is making the model get closer and closer to the truth. Okay, so this idea of things getting closer and closer to the truth, kind of convergent idea, is important. But then it's important on another level as well. Even when you set up your mathematical model, let's say of the climate there, so you define everything as mathematical objects, encode it all onto the computer in some way, set up the computer program and make it run. Well, the mathematical problem that gets set up there are almost always impossible to solve exactly. So they're not the kind of nice problems that you find in these tutorial sheets which pose a problem and have an exact solution. They're invariably these kind of objects called differential equations. So you get a set of equations which tell you things about a certain function and about the rate of change of the function, and your idea then is trying to predict values of the function at some future time. But the nature of these things is you can't get the exact solution out by doing a bit of algebra or whatever. They really can only, we can only solve the mathematical problems themselves approximately. We refer to these as numerical solutions. Okay? Now you'll be learning about that in detail in your second and third years, the numerical solution of ordinary differential equations and partial differential equations. So you might think that's really bad. We can set up these mathematical models, but we can't solve them. We can only solve them approximately. Now that's not a major drawback, because the way the solution techniques work mean that, in principle, although the solution is an approximation, we can make the approximation more or less as good as we want. Okay? It'll take more computing power, it'll take longer computations, but in principle, these approximate solutions we produce, we're able to control the amount of error involved and make them as close as possible to the real solutions. So again, we have that idea of an approximate thing through various iterations getting closer and closer to some kind of limiting state. And then another slightly different aspect of it, the way it rears its head, in particular this idea of divergence, is so slightly different from trying to predict the climate, but let's say we're trying to predict the weather. So the weather meaning what it's going to be like in the next couple of weeks. So again, the Met Service or whatever, they have a computer model of the atmosphere about what's going on. They input into it the idea of the physics of how the atmosphere works, how the energy comes from the sun, etc., etc. They input into it all their best observations of the current state, where the clouds are, where the warm air is, where the cold air is. And then they run the computer model, run it forward a few days to give a weather prediction for a few days. Now, no matter how good the model is, no matter how big the computers are, what we know and what seems to happen is that, well, we can give quite a good prediction for tomorrow. We can give a very accurate prediction for 2 days hence, 3 days hence. But like as soon as you start to get like longer than 3 or 4 days, definitely once you go out beyond a couple of weeks, the predictions made by the computer model become less and less accurate. Okay? We're less and less confident in the predictions given by these weather models the further forward in time we try to predict them. So there you have the idea that this kind of process or this kind of sequence of predictions for the 1 day out, 2 days out, 3 days out, etc., is probably going to be diverging from the truth, from the actual situation. Now that is kind of linked to this idea of chaos in dynamical systems or in physical systems, which you'll learn about in one of the third-year units if you take it. And this seems to be something that you can't get over by just throwing more computer power at it or trying to make your model more detailed. It is kind of some kind of inherent thing in these systems. The tiny little differences, the tiny little discrepancies in initial data can have large effects when the model is run for any amount of time. Okay. Any questions or points or queries just on that? Yes. Oh yes, yeah. They're not right now, but that will appear in Moodle. Yes, so there's no need to take those down. So, yeah. So that's just some introductory comments about why, in a wider scientific sense, the idea of convergence is important. But of course, we're mathematicians, so we're primarily interested in these things for their mathematical factors. Okay? So convergence and divergence is also all over the place in mathematics. One place to see it or appreciate its importance is when we look at the different number systems. So some of the most familiar systems of numbers that we have, well, we have the integers, and these are normally represented by a z. It comes from the German Zahlen for number. But the integer z, so those are the counting numbers, 0, 1, 2, 3, 4, 5, etc. There's an infinite number of them, and all their negative counterparts. Okay, those are not too hard to define or, get a grip on mathematically. But then, of course, we also like to measure quantities in between all those integers. So we have all the fractional quantities. Every fraction you can form is n divided by m, where n and m are two integers. That's what we call the rational numbers, and those are traditionally represented by q for quotient types. Now these are examples here of set notation. We read it in English as z is the set of elements -3, -2, -1, etc., etc. Q is the set of elements. Every element you can form, which is a fraction n divided by m, and what are n and m? N and m are any integers, with the condition that m is not the zero integer. Those are examples of what's called set builder notation. And set theory is the first topic that Saeed will be talking to you about. So you'll be learning all about that kind of notation very, very soon. Okay, the integers and the rationals, they're still, they're some of the most immediate number systems. They're not that hard to get a handle on. But then mathematicians pretty soon discovered that these aren't all the kind of numerical quantities that there are. There are other kind of stranger numbers in a sense, things like the square root of 2, pi, and the e, the root of the natural logarithm. Now these numbers, these quantities, they're certainly not integers, but they're also not fractions either. Okay, the ancient Greek mathematicians were aware that the quantity, the square root of 2, could not be written as a fraction of integers. And later on, I'm not even going to pretend to know off the top of my head. Later on, proofs were provided. I mean, much later on, I think into the 17th, 18th, 19th, probably pi was proved rational. I'm sure it's the 19th century when pi was proved to be irrational, maybe even the 20th century. But we now know that numbers like pi and e, these other important quantities, those aren't even irrational numbers. So getting a handle and being able to describe so these are examples of irrational real numbers. How can we quantify these numbers, or how can we approximate these numbers, or describe features of these numbers? Well, we can do it using the integers and the rational numbers by setting up convergent sequences that get as close as we want to these stranger irrational numbers. Here's an example of one. Now, we're not going to be able to understand this or discover this for ourselves in this unit. We will encounter this in a second year unit when we're looking at Fourier series. But for instance, this is an example. It can be proved that if you take all of the odd integers, 1, 3, 5, 7, 9, etc., you consider their reciprocals, 1 over each of them, and you add them all up in an alternating fashion. So you have 1 minus a third, plus a fifth, minus a seventh, plus a ninth, minus 11th, etc., etc. And I have a dot, dot, dot there. The process never ends. You keep adding these little quantities. Now you're adding a positive bit and then a negative bit, positive bit and then a negative bit. The bits you're adding are getting smaller and smaller. Yeah, they're fractions, 1 over something, and the something is getting larger. So you're stepping up and stepping down in value all the time as you develop this sum. So that already you can maybe taste or appreciate how that is going to be a convergent sequence. If you're tracking a level and you're moving it up and down, but the amount you're moving it by is getting smaller and smaller each time, you're going to be zeroing in, aren't you? You're going to be converging in on some limiting quantity. Now, we'll be defining these concepts and talking about these things very, very precisely in a few lectures' time. But it can be proved that this infinite process is getting closer and closer to the quantity pi over 4, which is a kind of a really weird and mysterious thing in some ways when you first encounter it. But you see, the elements involved in the series are very easy to understand. They're just simple rational numbers, 1 over an integer. And you're either adding it on or taking it away. At any finite stage, if you stop this infinite sum at any finite stage, all you've got is some kind of rational number. And it will be very, very close to pi over 4. Very, very close to a quarter of pi. So if you multiply it by 4, you'll get something very, very close to pi. And the longer you develop the sum and then stop it again, you'll get something even closer to pi after you multiply it. Okay? So that is an example of an infinite process, this infinite sum. This symbol here is the Greek letter sigma, capital sigma, which is what we use to represent a sum. Sigma, S for sum. And you're summing from n equals 1 to infinity. So it's an infinite sum. That's an infinite process which is converging, getting closer and closer to the limiting value of pi over 4. So convergence is everywhere in kind of science, mathematical modeling setup. It's inherent in number systems and the way we construct more complicated number systems out of simpler ones. And of course, it's very, very important for the study of calculus. Study of calculus where you're looking at rates of change of functions, or you're looking at what happens when you accumulate functions, when you integrate them. Convergence is very, very important there, okay? Because the rate of change of function is what the action of the function is doing at some instantaneous moment. And we approximate that by looking at what the function does between two separate time points, and then studying what happens when those two time points get closer and closer together, when they converge towards each other, what the change in value of the function is doing. Okay, so there's lots and lots of convergence everywhere, and we're going to study it mathematically. Okay, now with all that introduction, I haven't left ourselves a huge amount of time, but we'll meet some initial we'll meet some initial terminology now in the last few minutes, and then when I see you on Thursday, we'll do some more practical things, a lot more examples on the board, and more actual engagement with these things. So our first definition is simply to talk about a sequence of numbers. The infinite processes that I've been alluding to, our first example of it is as simple an infinite process as there can be, with just an infinite list of numbers. So that's what we mean by a sequence in mathematics. Okay? The ones that we look at in this unit, they're almost always going to be sequences of numbers, sequences of real numbers, numbers that come from the number line. So any kind of one-dimensional numerical quantity. If we want to talk about them in abstract or represent them just on the page in a general way, what we normally do is use a single letter for the elements of the sequence, this x, and we put subscripts on. So x1 is the first element, x2 is the second element, and so on. Okay. When you see a subscript on a letter here, you just read it in English as x4, x3, etc. So we can suggest the infinite sequence like this, giving the first few elements and then putting a dot, dot, dot after it. We can also represent the whole sequence as an object. And this is something we like to do in mathematics, just take this infinite collection and just, in our minds, bundle it up and refer to it as one object. So the way we refer to the sequence as a whole is using this kind of notation. So these curly brackets here, put the general element in here with the general subscript, so xn here. And then on the outside, we give some information about n. Subscript n equals 1 indicates it's starting at the value n equals 1. And the superscript infinity there means, well, it goes on without any end. Okay? We could refer to a finite sequence by, let's say we had a 10 here in place of infinity. That would be referring to a sequence of 10 elements, x1, x2, x3, x9, x10. The starting value n equals 1, ending value at 10. Now, finite sequences aren't particularly interesting. It's just a finite bunch of numbers. What we're primarily interested in is looking at infinite sequences and looking at their convergent or divergent behavior. Okay, let's just meet the first few examples just to look at the kinds of things we might put down as sequences. So you got the sequence of integers themselves, sequence of positive integers. So the rule, and very often we like to give a rule for the sequence, some kind of formula. So we can write Zn equals n. Very simple formula. The nth element of the sequence is the number n. There's this well-known sequence called the Fibonacci sequence. It begins 1, 1, 2, 3, 5, 8, 13, etc. Typically represented by f, f for Fibonacci. And the way that's defined, well, it's not defined by a single simple formula in terms of n, in a way, but it is defined by providing the initial two terms, just declaring that the initial two terms are both 1, and then giving this kind of rule. Now, this is called a recurrence relation. We say that the nth element of this Fibonacci sequence is the sum of the previous two. So your first task is to understand the way the notation is being used here. Fm, that's the element of the sequence at position m, is defined to be the sum of the element at position m minus 1 and the element at position m minus 2. So the previous two elements to Fm. So you can see that's what's going on there with the start of the sequence. 2 is the sum of 1 plus 1. 3 is the sum of 2 and 1. 5 is the sum of 3 and 2, etc. So we'll be interested in studying the behavior of recurrence relations and being able to tell when recurrence relations are convergent and when they're not. Is this recurrence relation, is this sequence, the Fibonacci sequence, is that convergent? Are the elements in the sequence getting closer and closer to some final limiting value? No. They're just increasing. They keep getting bigger and bigger. You keep adding larger and larger steps to them, so they're just zooming off without end and without any upper bound. So that's our first example of a divergent sequence, I guess. And the first sequence, Zn equals n, that's a divergent as well. Then we could have the sequence of odd positive integers, an equals 2n minus 1. So the odd integers, 1, 3, 5, 7. Here's a question for you. Another interesting sequence, and this is one we study very much so in the second year in the number theory unit. It's a sequence of prime numbers. Everybody should know what the prime numbers are and be able to name the first however many of them. 2, 3, 5, 7, 11, 13. So we normally call those the sequence P, P1, P2, P3, first prime, second prime, third prime. Now what's the formula for this? How is the nth prime defined in terms of n? It's a good test. I'll be very impressed with the student who tells me the answer to that. Is it 2n plus 1? No. Why would I be very impressed? Because we don't know. So that's the correct answer. Nobody knows. And more than, not the fact that we don't know what the formula is, we know that there is no kind of simple kind of formula that can go here. Okay? The primes, although we know a lot about how often they occur, we can never say precisely when they're going to occur. So there are a whole bunch of results of proof. There is certainly no polynomial that you can write down. There's no polynomial in n. Even if you allow yourself, huge polynomial, lots and lots of terms in it, complicated coefficients. There's no simple polynomial in n that you can write down that tells you what all the prime numbers are. Okay? So it's certainly it's a sequence we like to think about and talk about, We do know that it's infinite. We proved that in the second year. There are an infinite number of prime numbers. And given any number, we can test whether it's prime or not. It may take us a long time to test it if the number is very big, but we can test it. We can answer the question of whether it's prime or not in principle. And so it's a perfectly good infinite sequence, but there's no kind of simple formula or rule that it can describe. Okay, good. Okay, I won't rush through too much more stuff. So we'll continue with this material tomorrow afternoon. Don't worry, we will be getting a lot more involved in maths, and I'll be hitting you with a lot more problems. You can already see some of the problems there in your tutorial sheet. The first few are quite straightforward. When you go to the back, I think you'll appreciate we are going to meet some quite challenging things. So there's lots here to get to grips with. Lots of frustration embodied in this sheet, which is good. Lots of struggle, which is good. Okay?